aiming to focus on is having a good discussion around kinetic energy thresholds, which is a very fancy term for just basically how much force within a crash we as humans are able to withstand before fatal or serious outcomes occur. So that's what the kinetic energy threshold really reflects. That's the definition of it, just how much force we're able to withstand. We'll also talk about different environments, specifically intersection and mid-block locations, and talk about some common risks associated with that, as touched on earlier. Make sure you're counting your wallies, because that will be included in the quiz at the end of today's session. So make sure you're on the lookout for our little pal there. You should be on one wally. Okay, intersections. Now, this is, I suppose, one of the common crash types that you'd be expecting to see when we do have intersection crash types, which is referred to as a cross intersection or a T-bone style crash. Basically, the front of the vehicle colliding with the side of the vehicle. All the wonderful safety benefits of the motor vehicle is within that front section. One of the weakest points of the vehicle is the side of the vehicle. So I'm sure Ken would have explained the vehicle that is colliding and doing that damage, that's referred to as the bullet vehicle. And the vehicle that is struck in the side impact there, that is referred to as the target, which is an unfortunate term, but bullet and the target vehicles there. This is not the only type of collisions that can actually occur at intersections. So what can occur, other crash types within intersections that we do see, relatively high numbers of, is secondary collision. So a first collision could look something like this, and then either the bullet vehicle or the target vehicle, they get pushed off into the roadside environment where there could be fixed hazards. So unfortunately, a lot of our intersections do have lots of fixed point hazards, things like signal pedestals or utility poles, even signage, depending on how big the sign is and things like that. But there's generally lots of things for errant motorists to actually collide with, which is not a great outcome. So those secondary crashes can also be a concern at intersections. The other crash type that can occur within intersections is like sideswipe crashes, basically failing to maintain your traffic lane and accidentally, veering off into an adjacent lane, having those sideswipe collisions. Those sideswipe collisions, generally, they are not as severe. They are basically, minor fender bender type issues, unless it does involve, a secondary incident there where you're actually getting pushed off the road and into that roadside furniture. So there's a few different intersection crash types that can occur. Generally, though, the one that we are most worried about is this cross intersection or this T-bone type. The Monash University Accident Research Centre, or MUAC, they were contracted to complete some work and investigate, well, what are the kind of principles that we should look at to reduce trauma at intersections. Very interestingly, the first two principles were to do with, well, if we can remove vehicles, or at least reduce the number of vehicles going through there, or remove or reduce the number of intersections. They were seen as the two salient points, because basically the configuration in itself is not conducive to safe outcomes. Both of these points relate to the exposure. So Ken would have been speaking to you about this idea of exposure, likelihood, and severity. When you're reducing the number of vehicles through an area, you're actually influencing the exposure. So both of those actually relate to exposure. Number 3 point that they've identified as part of this study. Oh, sorry, Loretta, do you want to jump in?
I just thought, just while we're on that, in regards to the, bullet and target vehicles, there's a question that's come in. In a few seconds space, the bullet vehicle and target vehicle can be swapped, isn't it? Then the impact angle can be worked out twice for each scenario.
It's a good question. So there are multiple ways in which that secondary collision could occur. So the initial, you're right, like bullet and target starts off like that, but then from that point on, the bullet could potentially get, or, veer off and then collide with a fixed hazard, and then, having a significant point source impacts associated with any of the roadside furniture. As part of an SSA, it's unlikely you'd be going into the specific crash analytics of every possible situation or scenario that could occur. SSAs tend to be a bit higher level, focusing on that, that really significant impact, which is that 90-degree cross intersection crash, and kind of taking that as the crash that would be reviewed. It'll make more sense once you have a look at the SSA matrix and things like that. But yeah, you don't tend to get highly involved in all the possible scenarios that could occur. Otherwise, it would just be a massive, massive onerous project. Anyway, number 3 point here is fewer conflict points per intersection. Basically, what this is saying is if you're able to influence the number of traffic lanes, that would then reduce the number of conflict points at the intersection. So simplifying the intersection there to reduce the likelihood of trauma occurring there. And that one would be referencing the likelihood. So if you've got fewer conflict points, it's less likely for that collision to be occurring. Impact speeds and impact angles constrained to biomechanical tolerable levels. This is another one of those fancy words. It's the same term used before as that biomechanical thresholds. It's basically how much force we as humans can withstand before serious trauma occurs. So basically reflecting on the speed environment. And that's not just the posted speed, but what is the operating speed? What speed are vehicles traveling through there? And considering the angle of that collision as well. So they've done a lot of research within this space to have a look at what are some of those speeds and angles that would be survivable. This 4th point here would relate to severity. So the exposure was just the number of vehicles. The likelihood was how many conflict points we've got. Severity, what we're looking at is what speed is the collision likely to occur, and what is the angle of that collision. They managed to condense this research into this table here, which is basically acknowledging what are those biomechanical threshold levels. And it's saying if you've got an impact speed, that is the bullet vehicle impact speed, if it's at 40 or below, it's likely within that survivable range, regardless of the angle. So even if you're coming at 90 degrees, which is the worst, it's likely to be survivable. Some people may actually not survive that, depending on their health and age and demographic and things like that. But this is what their research concluded. The impact speed of 50 kilometers per hour, that is where we're seeing the maximum angle that we can survive at that speed is about 90 degrees. So that's the perpendicular crash. So that also supports the research, which was those crash curves that we showed in the previous module, where basically if you've got a potential for a 90-degree crash, anything that's 50 kilometers per hour or higher, there's an exponential increase in the risk of a fatality. If we've got an impact speed of 60, you want to have angles that are more acute. So this is no longer a cross intersection, it's a skewed intersection. So 52 or 128 degrees. ChemX, that is just the software that they use to actually produce this kind of information. And what this is referring to is if you've got a crash rather than at 90 degrees, but something more like this, you can actually have slightly higher speeds because they're kind of glancing off of each other and they're able to dissipate some of that energy over a longer distance. So it's not just an impact like that where it's straight into the side and there's dramatic deceleration. You've got more of an ability to kind of gradually decelerate over time. So 60 kilometers per hour for more of those skewed types of intersections. 70 kilometers per hour is when we're looking at things like rear end crashes or head on crashes. So the 0 is just indicative of head on, and anything that's over the 180 is indicative of the rear end type of collisions there. So we tend to take 70 for our head-on type of collision, which once again supports that crash diagram that we looked at on Tuesday. Interestingly, anything above 80 is not survivable for the human. We're just not built. We're not built to be able to withstand those types of forces unless you've got like an edge barrier containment system that is deliberately designed to be able to contain an errant vehicle and gradually slow that vehicle down. You can certainly get higher speeds for those scenarios, but in terms of vehicle-to-vehicle collisions, unable to survive anything above that. And we've certainly got lots of the network that has higher speeds than 70 kilometers per hour where there are those intersections. Loretta.
Some great interaction here in the chat, but there is a question just in regards to the 90 degree. What's worse than 90 degrees? Is that what's covered in all okay?
No, so 90 degrees would be the worst. That's the worst place that you could possibly hit another vehicle at the intersection. So these are all intersection crashes. So we're not considering other, mode users in there. So this isn't collisions with pedestrians or cyclists or anything like that. This is vehicle-to-vehicle collisions and those impact speeds and angles.
Thank you. Another question. Does the 52 degree and maximum impact speed of 60 versus 50 kilometers for 90 degree prove why roundabouts are safer, i.e. higher deflection angle?
Bang on. That's great. I'm glad that you noted that. So let's give a prize out there. And that's one of the reasons that we love roundabouts is because of that angle that it creates. That impact angle is just much more favorable. It sounds weird that you want to be hit in any kind of scenario, but if you did have to get hit in a car and you're in a car, you want to make sure it's at an angle like that so you're able to gradually dissipate that energy. So roundabouts are excellent in doing that, providing that angle of collision. Roundabouts also, they tend to reduce operating speeds because in a traditional intersection, say if it was signalized or something like that, if you had someone running the red light, very likely that would be at quite high speeds. You put a roundabout there, it's very good at reducing speeds. So there's less of a chance of a vehicle just driving straight through that and having a quite high speed crash occur. So just looking at this as an example, if you were doing a design and you were looking at, implementing a T intersection or a new intersection or new access or something like that, it'd be quite easy for you just to draw out the potential movements of vehicles. So in this instance, we've got a vehicle exiting. I'll use a different color so it's a bit easier to see. Try yellow. We've got a vehicle exiting and turning right in this instance. Collisions with through traffic in this regard could be about 104 degrees. It's quite specific. For the purposes of an SSA, you would basically just assume that that's close to 90 degrees. So you'd be looking at that 50 km/h impact speed. And if it's higher than that, then it's likely to have quite serious outcomes. But collisions with this traffic lane is closer to the 27-degree mark. So that's where you've got more of an acute angle, and it's actually a more favorable crash condition. So potentially you could have higher speeds for that leg. Now, this is kind of theoretical, just to get your understanding of how impact speeds and angles could be adopted. Generally, though, if you were doing an SSA and looking at this intersection, you just simplify it and you just say, there is a chance for those 90-degree crash angles to occur. Therefore, the crash speed or impact speed tolerance that I'm concerned about is around the 50 km/h mark. So you don't need to get quite into this detail. Collision angles. So yeah, that's just more about, kind of vectors or understanding the direction of travel for both of those vehicles, and also considering any of those secondary collisions that could occur. Don't need to get too hung up on this one either. A collision study was produced. Basically, this one was an analysis of lots and lots of police reports from different jurisdictions. And what it kind of discovered was, if you've got a vehicle at the bottom of the screen there and it's heading towards an intersection like that, you've got another vehicle heading towards an intersection like that, and they are colliding at the intersection, what this graph is showing, or this diagram is showing, is where those secondary collisions tend to occur. So you've got the angle that's shown on the outside of the radius, and then each of these are like distances that goes up by 5 meters. And it's basically most of the trauma occurring in that, top right-hand area. I think it's pretty self-explanatory as to why that would happen, because you've got two cars going in like this, they're going to naturally get pushed out in that top right quadrant. So it kind of makes sense rationally. Not sure you needed a study to kind of prove that. But anyway, it's basically, if you've got fixed hazards within that top right quadrant, that's where you're likely to see vehicles getting pushed into that area. We'll do a little exercise about intersections, just so we're all speaking the same lingo, and we can have a bit of a go at working through a real example of an intersection. So putting on that, intersection, impact, speed, and angle hat, and just going through that information we've just covered. If we were looking at an intersection that looks like this, what are some of the risks that you might kind of identify? Now, the exercise is coming up in a few slides' time, but I'm just going to talk through what this intersection context involves. So this north-south leg, the main thoroughfare, is an arterial road. There's about 22,000 vehicles a day. The minor leg here is a local street. It's primarily used for residential access, although there is a school about a kilometre down from here. This one has about 2,000 vehicles a day. The speed on the local street is 50. The speed on the arterial is 70. The only current control in place is a give way for the local street, and all turning movements are permitted. So you can turn left in, left out, you can go right in, right out. As you can see, all of those turning movements are permitted. There's a little service road on this quadrant here. It also continues on the other side of the intersection, and it's actually a two-way service road. I'm not going to be too focused about that area because the predominant crash risk is the arterial intersection. So the service road, you can consider it as part of this exercise, but the focus should be the arterial. Now, speaking of crash outcomes, this intersection has seen 6 crashes that have occurred in the last 5 years, and they are all relating to this type of movement. Either the vehicle as it's exiting collides with the right turning vehicle in, or a through traffic in that way, not the right turn, ignore that one. 90-degree angle crash going that way, or 90-degree angle crash going that way, right? So that's the 6 crashes that have occurred. 5 of them were serious injury crashes, meaning it was hospitalization. 1 of them was an other, so minor injuries. The other thing to note about this specific area, just to help with your understanding of the characteristics of this environment, there's a bus bay here. So heavy vehicles run along here, buses quite frequently. I think it's about 12% heavy vehicle population on this north-south arterial. There's a shared use path on this side. It doesn't really connect very well across. And for those that may have noticed this giant culvert-like structure, it's just obviously for drainage. It looks really, really big on this aerial, but it's about 1 meter high or something like that. Few other things just to set the scene. The shoulders also double as bicycle lanes, so you've got cyclists within this space. That's all I can think of at this stage. I'll show you some images on the ground now, how this site looks. And that's the minor leg to the right there. You can see that the bus shelter, the bus bay is there on the left. You can kind of see there's a little bicycle symbol there for the bicycle lane. I'll show you another photo now on the other side of this intersection. Looks like this. You can see the shared path. It's over there on that parkland area. There's no barrier system or anything like that to protect from that culvert, so it's just a curb system being used there. Generally, this is what it looks like. I'll check in with Loretta to see if there's any other questions that participants might have about this site before we get into the exercise.
Yeah, perfect. Thank you. Just in regards to the intersection further south, that is causing traffic to queue up on the side street. If there is there any known queue frequency?
The next intersection
north. Sorry,
south.
north.
Okay, the next intersection south is about 1 kilometre away, and the next intersection north is about 400 meters. No significant concerns about queuing from either of those intersections.
Thank you. Some good input in the chat, but Max will go through the specific instructions on what to include in the chat shortly. Thanks.
So the exercise for everyone here is I want you to remove fatal and serious injury crashes at this location. Sounds pretty straightforward. I want you to put on your design hats and think of what are some of the treatments that we could potentially implement to remove the risk of serious trauma occurring here. I am going to constrain you though. I'm going to give you a $3 million budget. Now, if you don't know the cost of specific infrastructure items, just put in the chat cost for, and then just, put a question mark next to it. And I'll give you, an indicative cost. So for instance, if you wanted to know what the cost for a roundabout at this site is, you could type in the chat cost for roundabout, and then I would tell you a roundabout at this location is going to be $9.1 million because it's going to involve land acquisition and lots of utility changes. So that is above your budget. So unfortunately, no roundabouts here. A couple of other constraints is we cannot close the intersection. So we have to maintain the existing turning movements. In other words, it still has to be left in, left out. It has to be right in, right out. We're unable to shift that. Okay, so we can't do anything there. The third constraint is we need to operate within the current political framework. And this one is basically just understanding of what would likely be feasible. So for instance, if your suggestion was, we are going to slow traffic down to 10 kilometers per hour at this intersection, politically, I don't see that one getting the tick of approval. So that one wouldn't pass the pub test, so to speak. So just want to make sure that we're looking at pragmatic solutions here. Within all your recommended treatments that you're welcome to type into the chat, I want to make sure that you are clarifying if they affect exposure, likelihood, or severity. So basically, whatever you type in, at the end of it, just put in brackets if it's E for exposure, affecting exposure, if it's L for likelihood, or its severity. And it very well may affect one or two or three of those attributes. But I just want to see how people are starting to categorize those different treatments. I'm going to give you, let's say, 3 minutes to have a good think about this one and pop down in the chats those treatment options that we could look at. Loretta.
We've already had a couple of questions in regards to the costs.
Good.
Yeah, cost for signals, and yeah, signalized intersection with raised safety platforms.
Oh, okay. So let's just say cost to signalize this intersection. I'll do you a good deal and I'll do it for $1.5 million. If you want to do raised intersection as well as the signalized intersection, I'll do it for $2.85 million. That's a bargain. That's a good deal. I'd take that up, Loretta. What else have we got? Cost of lights, street lighting. So I'll go back to the image just so you can have a look if there was existing lights. We do have some lights there. Perhaps we want to upgrade them, increase the brightness, change over the luminaire heads, or increase the spacing, decrease the spacing, so that you've got more illumination there. I'll do that for $650K. I'll give you just 1 more minute. I can see lots of answers coming through, which is excellent. Remember to put in the ELS. I like that people are also putting in their own costs. That's great. Don't trust me, get a second opinion. Give you 30 more seconds and then we'll go through some of these treatment suggestions. What's the cost for merging lane turning right? It's got to be a little bit of widening there to be able to do that, to facilitate that. So I'll do it for $875,000. All right, it's good. There's lots and lots of good discussion there, and I'm enjoying the treatments that I'm seeing there. Those that have suggested a seagull type treatment, I'm just going to draw that one out for those that are not familiar with that term because it's not an overly common type of intersection arrangement. I'm actually really bad at drawing seagulls. It's this idea of if you were turning right out of here, right? So say you're a vehicle turning right out of here, you get this kind of acceleration lane. So this is kind of blocked off. It's just curbed. And then you pick up speed, pick up speed, pick up speed, and then you enter the traffic lane. Like that. The same thing is done for this lane here. Enters there. That's called the seagull intersection. Now, from a impact speed and impact angle approach, the seagull is really, really good because we no longer have a 90-degree crash angle. You're actually getting a crash angle that's much more acute, which we were saying is much more favorable. You would also have speeds that are relatively similar as well. So the delta V, which is just the change of velocity or the change in speed, is less. Sorry if that's too physicsy. But basically, if you've got two vehicles going at similar speeds and it's a low crash angle, you can actually get quite high speeds. They can be quite manageable. You do need to be mindful of if they're going to then, veer off into the roadside and then hit a pole or something like that. But generally, the impact speeds and impact angle work quite well with seagull treatments. The disbenefit associated with the seagull is that kind of merge it's really uncommon and it's also hard to do. If you were doing that right turn, you need to look over to your left to see there's a gap in traffic, which is super uncommon. And for those senior citizens or people with issues twisting their neck around, there can be a bit of a, well, I'm just going to go for it. And there can actually be an increase of likelihood of crashes actually occurring there. So it's an interesting treatment, and I like that it was mentioned. New Zealand actually has a seagull prediction tool, which you can, put in your intersection configuration, speeds, traffic volumes, and things like that. And it basically says how safe it's expected to be, or the safety performance of that seagull if it were to be installed. So if you are looking at that, I'd recommend getting a hold of the New Zealand tool there. That's enough talk about seagulls, though, as a really interesting suggestion. Compact roundabout. That's very interesting. So I did say that we couldn't do the normal roundabout because that's going to be too expensive because it's going to involve lots and lots of land acquisition because it's a large footprint. Compact is making it a much smaller footprint, and I've got a few slides that's going to talk to that point in an exam. Sorry, in a few. Got an example in a few slides that is going to talk to that point. Let's see what else we talked about here. So dropping the speed, yep, bringing down the severity and the likelihood. I like that suggestion because I gave you a $3 million budget and you spent about $800. So that's good. That's good value for money. I think that would be quite a positive BCR. You need to also reflect on, just because you're putting up the 60 km/h signs, what is the actual operating speed change? So you might not actually see a significant reduction in speeds there, but I like the idea there. Few people discussing, well, let's put a barrier system to protect errant vehicles from the culvert, and I think that's very, very sensible. When we are looking at barrier systems, so let's just say I've got a barrier here and a barrier here, we tend to categorize edge barriers as just affecting severity. So if you've got a barrier system, it would only be the severity. Basically, previously there's no barrier. It could be quite a serious outcome because vehicles are going straight into an open ditch or an open culvert. Quite high severity. If you put the barrier system in, it's likely to be able to contain that vehicle, so you don't have that serious outcome. The likelihood, though, isn't actually changed because it's just as likely for a vehicle to run off the road there. In fact, you could argue that it's more likely for a run-off road to occur because if you put it really, really close to behind the back of curb, you might have those nuisance impacts. So it could potentially be increasing the likelihood. So that's just an interesting little aside. But generally, you just record barrier systems as reducing or affecting the severity of a crash. I'm not going to be able to get through all of those comments, but I like what I saw. I'm just going to run through, I suppose, some of the common themes associated with treating this intersection. Traffic signals. Now, that was one of the first treatment recommendations that came through, which is fabulous to see. The crash reduction factor associated with traffic signals is around about 45%. So the number of crashes you're expecting to reduce with the implementation of traffic signals is about 45%. It affects the likelihood. So it's done nothing to the traffic volumes, so the exposure remains the same. It does nothing for the severity because the speeds and the impact angles are the same. Traffic signals do not slow down traffic, obviously only when there's the red phase, but there's still that potential of red light running, therefore the potential for those high speed 90-degree angle crash types. So very, very important for traffic engineers to understand that traffic signals do offer safety benefit, but they do not completely eliminate the risk of fatal and serious injuries. In fact, just as a demonstration of this, this is a heat map of fatal and serious injuries that have occurred kind of in the southeast of Melbourne, near to where I live, coincidentally. And the heat map, the brighter the dot is just indicative of where we're seeing clusters of crashes. Every single one of those clusters are signalized intersections. So there has been this opinion that traffic signals are the best thing to do for any unsignalized intersection because they are going to solve the issue of trauma there. They do not solve the issue. They will improve things, and it's important to understand that they make things better, but they are not going to get to that ideal state where we are aiming towards zero. They're not going to virtually eliminate the risk of fatal serious injuries. So it's good to be mindful of that. Ability to influence the likelihood the severity remains the same. Compact roundabouts. Is this one a compact? Let me have a look. No, this one is just a regular roundabout. So this one, as you can see, involves quite a lot of land acquisition. We already talked on why we like the roundabout is because if we do have a collision occurring here, the kind of angle that that collision occurs is much more favorable. And what I also spoke about there is if you put a giant circular island in the middle of a roadway, it's very, very good at waking up drivers and forcing drivers to slow down. So it's very good at reducing severity because it is impacting or affecting the impact speed, impact angles. All right, smaller roundabouts. So this is obviously a very, very different road environment. This is local streets, also a different jurisdiction. But using that kind of roundabout thinking, but not having to build out lots and lots of traffic islands and things like that to be able to accommodate that movement. So in this instance, it's actually just paint that has been used to demarcate that central area. So if you were turning right, you know, it's likely that you'd just drive straight over that thing. And that's okay. What this has done though, is it no longer assigns the priority to one thoroughfare. So rather than just saying, this is the thoroughfare, this is the thoroughfare, and these guys need to yield, it's instead saying everyone that approaches this intersection needs to slow down and yield. Very, very similar concept to the four-way stops that North America employ in their thousands, tens of thousands. We've got a few examples in Australia of the four-way stops, and they work very well because you no longer have this assumed priority that I can just drive through here, everyone else needs to yield to me. It forces motorists to slow down, and in doing that slowing down, they're already reducing that risk because if there were a collision to occur, it's at slower speeds. Loretta.
Just a question that's come in regards to the roundabouts, of course. Wouldn't a roundabout also reduce the likelihood of head-on collisions? And would the deviation not push vehicles away approaching from opposite directions?
Yep, absolutely. Roundabout does that very, very well. Very significant reduction in head-on crashes. And also, if there was a secondary collision, it's pushing it away from that opposing traffic stream. So, yeah, good pick up. We'll give a prize out there. Another thing that we can see with roundabouts to further reduce speeds is this the idea of actually incorporating vertical deflection on approach to the roundabout. So, you know, if you're unable to get enough speed washed off or speed dropping just due to the radius of your curves, well, you can implement vertical deflection, speed humps, speed cushions, things like that. So you're physically slowing down vehicles before they get to that comfort point. Once again, this is a local example, may not be appropriate for what we were looking at before. But if we compare our roundabouts to our traffic signals, and not just looking at the angles and things like that and the speeds, but they're also simpler in terms of where the collisions can occur. Don't get too hung up on the terminology, crossing, diverging, converging. Basically, all those dots represent where collisions could occur within a roundabout and a signal. And you can see there's a lot more dots within traffic signals just because there's a lot more conflict points within those environments. Roundabouts simplify that, less conflict points. We already spoke about this, but just to reiterate, The conflict angle as well is much improved for roundabouts, because you've got that acute type angle occurring, as opposed to that quite significant 90-degree perpendicular crash line. Now, going back to our traffic signals and, that discussion around why that's not the be all and end all. And the reason is traffic signals are still relying on human beings. So it's relying on the human being to be able to look at the red light, look at the red phase, and adjust their behavior. In other words, to brake, to stop. This isn't my time to go. We know that people get into cars in all types of conditions. So fatigue, they could be under the influence, they could be distracted, they could be thinking about other things, looking at their phone, myriad of reasons why motorists may fail to recognize that red. They could also be intentionally driving through red lights just to get home quicker or whatever it is. So there's those reasons as well. The roundabout doesn't care about those issues. It's much, much better at actually waking up drivers. It's very effective in just breaking up that monotony of traffic signal, traffic signal, traffic signal. It's creating that difference in the road context. And yeah, it's much, much better at activating your driver so that they are staying alert and they're aware of their surroundings. Just a note on turbo roundabouts. I'll show you what a turbo roundabout is on the next slide. But this is just an acknowledgement of the radius or the diameter of your circulating area does play a role in what types of speeds that can occur within your roundabout. So speed on the y-axis here, speed is actually quite a good proxy for the level of risk. The higher speed that you've got, the higher the level of risk. So you could also view speed there as the level of risk. And along the x-axis, we've got the radius of your roundabout that you're designing. So for a single lane or a turbo roundabout, I'll show you the turbo in a second. Generally, if you've got smaller radius or a larger radius, it's still quite good at influencing the speeds that can occur. Within double lane roundabouts, multi-lane roundabouts, dual lane roundabouts, whatever you want to call it, if you have a radius that's too small, what can occur is drivers just go straight through it, right? So it doesn't have the effect of impacting speeds. I might draw that on the next slide so you can have a look at what I'm talking about there. So this is an example of a turbo roundabout, and all it is within the circulating area, there's kind of channelized islands. So basically, if this was a traditional two-lane roundabout, and you wanted to go through here at speed, you could have just gone something like this, right? And that was what I was saying. If you make this radius too small, then drivers can just go straight through. So that's what that previous graph was talking about. The idea of the turbo roundabout is because you've got these channelized islands, which is just curb, just back-to-back curb, it's forcing drivers to actually use the radius of the roundabout, washing off the speed. There are examples of these installed in Australia if you're interested. This one's probably a clearer way to look at it. You can see those channelized islands there. This one's out of the Netherlands and admittedly looks incredibly confusing. This is just an arterial to arterial connection. And it looks like overkill. But the reason that this has been installed is because, you know, what we in Australia probably would have done is just set up a 90-degree cross intersection, signalized intersection. And no doubt we would have had massive amounts of trauma occurring just because you can tell this is a high speed, high traffic volume area. The Dutch, however, are a bit more safe system aligned in thinking, and they're acknowledging that, well, we can't just, you know, create this potential for serious trauma to occur. We need to look at ways to affect impact speed, impact angles. So they've designed and constructed this very, very large turbo roundabout. So if you're driving through here, you're really washing off speed because you're having to deviate around the roundabout there. Loretta, any questions on these roundabouts? I appreciate I'm going through this pretty quickly, and it might be a confusing topic.
No questions so far.
Okay, that's good. I'll go through some concepts now. So these have not been installed. Well, this one has not been installed, sorry. But it is an idea that could be used at future signalized intersections. And it's this idea of we can't just permit these types of movements that have a 90-degree crash angle. Instead, we want to ensure that vehicles are, you know, moving around here at lower speeds and at more favorable crash angles. So what's going on here? If you were going through, you'd have to kind of veer around like this, like that. And if there was another vehicle that was running the red light, well, they're going to be doing something like this. And it's pretty unlikely they'll be at high speeds if that collision were to occur, just because of the geometry of this. This is just a concept, as I mentioned, but yeah, it's got that safe system thinking embedded into it. I might pause here, Loretta, and give everyone a break before I chat through what was actually installed as part of that little exercise that we did there. So let's say a 3-minute break, go out, have a stretch, get some water, and we'll come back in 3 minutes' time. Back, everyone. Hopefully you all had a nice stretch, got to pat your pet or whatever you did. Just sort of comment in there that the outer lanes in this example could head straight through, and that is 100% correct. That could occur. Whoop. What happened? There we go. In this instance, you'd probably like to see this a turbo as well, so that you've got those channelized islands to reduce that as a risk. Excellent pickup though. Let's give a prize out there. Ben's also said there may be instances where the right turn traffic travel around the inner circle instead of going through. Yep. Right turn traffic travel around the inner circle instead of going through it. Oh, so like this instead of going through. Yeah, there's a few quirks with this one. As I said, it is just conceptual. I really think it would be very, very difficult to manage something that resembles a roundabout where you've got this many traffic lanes. Anything above 2, and it just becomes either a huge roundabout, and you do have the ability for that cutting straight across. So yeah, it's a tricky space to work in. Instead, what we could look at, which was mentioned in the little exercise, was raised safety platforms or raised intersections. Now, the idea behind this is we are slowing vehicles down through the use of vertical deflection prior to the conflict point. And that was actually the solution that was adopted as part of that intersection that we looked at before. It was traffic signals combined with the raised safety platforms. And I know a few people said that in the comments. So pat on the back for those that mentioned that one, or maybe you knew about this site. No, I'm sure that was all traffic engineering principles. The idea of the raised safety platforms, it functions very, very similar to how a speed hump would work in a local street environment. The difference is we don't have such a significant hump. The reason is, you know, if you were on a 70 km/h road and then you've got a 20 km/h hump, that's going to cause more issues and it's going to resolve safety things because you'd have vehicles kind of flying off Dukes of Hazzard style. So the raised safety platforms have a much shallower ramp. So it's just about washing off some of that speed prior to the conflict point. This is an artistic impression of that intersection that we were looking at. It's since been installed. And the raised safety platforms are only installed on that arterial, on the north-south leg, because we don't really need to slow down vehicles on the local street because they are the target vehicle. We want to slow down the bullet vehicle, the one that's causing the impact. So that's why we see the raised safety platforms on those legs. They are influencing both the likelihood and severity of the crash. So they're affecting the severity because they're reducing the impact speed. They're also influencing the likelihood because as you've managed to, you know, wash off some of the speed, you are also reducing the risk of a crash occurring. If you've got lower speeds, it's easier for vehicles to then engage in emergency braking to be able to avoid a collision. And it's also just gives, there's less distance that needs to be covered, you know, to get from velocity to nothing, as opposed to if you were traveling faster. So there's less of that deceleration distance. So it affects both the likelihood and severity. This is what it looks like out on the ground. So as you can see, it does look very, very shallow, but it actually slows down vehicles to about 50 km/h. So you can see it's advisory there. Here's another image of the intersection. Question for the group. Why do you think 50 km/h advisory speed was nominated for these raised safety platforms? So why do you think a 50 km/h advisory speed was proposed and implemented for this? There we go. T-Bone safe speed, suitable for a 90 degrees, safe system compliant. 50 is okay. Beautiful. So yes, it is acknowledging that it's reflecting back on those tables we were looking at before. Oh, I got a little hand clap. Looking at those safe speed thresholds or biomechanical tolerances. And we know that 50 km/h is around about what is survivable. Above that, not so good. So they've reflected on that and gone with the design. If we can bring these safety platforms to reduce speeds to 50 km/h, then we can significantly reduce the risk of serious trauma outcomes should a right-angled crash occur. This is one of Ken's favorite photos. Ken took this photo when he was out doing the road safety audit for this post-construction. The reason he loves this is we've got the green phase going for this through traffic, but we've also got the brake lights on. So we've got a vehicle that's actually slowing down prior to getting to a conflict point, which is pretty exciting. So if a collision were to occur, it's much more likely to be survivable there.
Do we know?
Oh,
do we know where that intersection is?
Oh yeah, this one is I shouldn't have written it out. Surf Coast Highway and Kidman Avenue. Surf Coast Highway, Kidman Avenue, just outside of Geelong. Any other questions around?
No, there was a couple sort of just in regards to the 50 kilometer versus the 20 kilometers. So should it not be 20 kilometers consistent with other road humps in regards to the...
So if you did it 20, because this is still 70, I actually got reduced to 60 as part of this project. But even if you're dropping from 60 down to 20, it's far too much of a speed reduction. And the steepness of speed humps on local streets are very significant. If you implemented that on arterial networks, every bus would be, you know, bottoming out, and you'd just be having lots and lots of rear end crashes. You'd also have potentially vehicles that would actively search for those speed humps so that they can get up and get some air and things like that. So there's lots of reasons not to actually implement something that's too steep.
Thank you. And just love Brandon's last comment. Ken should have been on the other side of the road behind the barrier. So yeah, well done, Brandon, for picking up safety.
We'll have to raise a non-conformance with Ken. It's good. Good pickup. The other cool little benefit of this treatment is when you're in this position. So when you're in the amber or the dilemma zone, as it's referred to, basically, if you're in a traditional intersection and you're in the dilemma zone, it just goes orange as you're amber as you're about to head through. You need to make that decision. Do I have enough time? You know, am I going to run the red light, etc. With the raised safety platforms, this vehicle has already got their foot on the brake. So it significantly reduces the dilemma zone because it's easier to be able to come to a stop because you're taking away that half a second from accelerator to brake. So there's a reduction in that dilemma zone there as well, which is pretty neat. We also have examples of raised safety platforms on larger roads. So this one is this one is Dalton Road. Can't remember the name of the intersection road. It could be Childs Road. Is there a sign on this photo? No, there isn't a sign. Anywho, this one is actually a really, really significant north-south movement corridor in Melbourne. Connects the northern suburbs, kind of goes all the way into the city. Lots of heavy vehicles that run along here and things like that. And yet this raised safety platform treatment was still implemented. So just wanted to highlight that there's a range of environments that this could be implemented on. It's not just about things with lower volumes or, you know, you can't have any heavy vehicles or things like that. There is opportunities to be brave, to be courageous and try and get these things further abroad in multiple different scenarios. This one also involved a slip lane. And vehicles were similarly slowed down to the 50 km/h on the slip lane. In a perfect world, we would have loved to have seen this advisory around the 30 km/h mark, because that's when we know we've got that significant increase of serious fatal outcomes for pedestrians. The reason that 30 wasn't adopted here is purely for consistency. So that's 50, that's 50. Didn't want to create different advisories depending on which part of the intersection you're coming from. But in a perfect world where you have potential conflicts with vulnerable road users, with pedestrians or cyclists, you'd be able to reduce speeds to around that 30 km/h mark.
Hey, Max, do you have a suggestion on what the best location is for a stop line near a raised platform?
Yes. And what I would reference is road design note 0307. So this is out of Victoria, but it's still pertinent to wherever you, whichever jurisdiction you're in. Generally, stop lines are put at the toe of the ramp. I'll go back to another. You can kind of see it there. At the toe of the first ramp. That may then push back the hold line of the intersection. So it could, push things further back and have other effects. But as with any treatment, you need to weigh up what are the risks associated with going for this as a proposal versus keeping things existing, and something to review as part of a risk strategy, I would suggest. But generally, they're installed at the base of the toe, or the toe of the ramp. I'll flick through that one. Very, very handy reference. Austroads has similarly completed a research report about this one. So lots of information out there. Lots of jurisdictions are implementing these. This one's in New Zealand. But it's very good evidence to suggest that these types of treatments are where we are going to see significant reductions in trauma. As I said before, CRF, crash reduction factor, for a traditional traffic signal, it's about 45%. Raised signalized intersection, we're about 85 to 95, 90%. So it's got a much higher crash reduction factor. We're not 100%. I don't think there's any treatment that has 100% crash reduction factor, unless it was grade separation. But even then, you've got the potential for people doing whatever they want to do. So 85% is truly an excellent CRF. All right, I'll show you this example of an intersection in a rural environment and some of the constraints that this site has. So we've got, it's a really strange configuration because the arterial road is actually here, and then it bends and goes across there. So it kind of dog legs, but it isn't set up to really support that. In other words, you've got a lot of right turning traffic here, just because that's the dominant traffic stream. That's the arterial road. Go to the next slide. Oh, there was a little graph there. I didn't have to draw it out. There we go. That's the arterial road. The minor legs, as shown, are the other legs there. This little hut is like I actually don't know the term for it, but it's a very, very important Telstra asset. And it would have cost millions of dollars to relocate that. So initially, they were thinking, we'll do a roundabout here. Let's bring down impact speeds. Let's improve impact angles. But that would have involved shifting this across into the paddock. And it just was not feasible due to Telstra being like, no, that one's really important for us. You can't touch that. So instead, they looked at this idea of compact roundabouts, which we touched on a little bit before, which is basically, rather than requiring reverse curves that come into a roundabout traditionally, and what I mean by reverse curves is, I'll try and draw it on top of this image. The way a conventional roundabout would work is, if as you're driving up, you get, I've really exaggerated it here, but you kind of get chicaned or get horizontally displaced left and right. So as you enter the roundabout, you've reduced your speed, right? So it uses horizontal deflection for that speed impact. That's referred to as a reverse curve. Those that are familiar with that term. A compact roundabout, and I should just say, because of that reverse curve, as you can see, it takes a lot more space. And similarly on this side, if you're doing reverse curves, you'd be eating up that thing, and it has a much wider footprint. So rather than use horizontal deflection, rather than that chicane, the compact roundabout uses raised safety platforms or vertical deflection to be able to slow down vehicles before they get to the conflict point. So in this scenario, what actually happens is you're going at 100. Remember, this is a rural environment, 100 kilometers per hour, and you hit this raised safety platform first. That one drops you down, I'm gonna say, to about 80. I can't quite remember at the top of my head, but it's quite a gradual reduction, right? So you go down to 80 kilometers per hour, and then you get closer to this one here. And once again, there's another speed reduction with the raised safety platform there. That one's to 50 from memory. So you kind of got these two different approaches, and you can see that's consistent on all of the legs there. You don't actually need the raised safety platform on the departure side, or at least not the initial one. So as you're exiting the roundabout, you can just continue with your speed there. You don't need to be slowed down again because you're not approaching that conflict point anymore. So this is what you could use where you do have those constrained sites, because it is actually cheaper to be able to build within your existing footprint, not have to worry about land acquisition. And even if it does involve raised safety platforms, which is obviously additional asphalt, much cheaper to put in more asphalt than to be buying up land or moving utilities. I got a little video here that shows a little fly through of this compact roundabout. So we'll have a look at this one. You can see the initial raised platform, and then there's just a straight section. And then there's the additional raised safety platform prior to getting to the circulating area or where the conflict point is. All right, Loretta, shall we do a quiz? Let's do a little poll, make sure everyone's staying with us.
Yep, sounds good.
Okay, jumped up on my screen. True or false, traffic signals are not safe system? True, false, unintelligible question. I'll give you 30 seconds to have a go at that one. That site that we just looked at as well, what is the name of that one? That's Coonawarra Leongatha. You just type in Coonawarra Leongatha and then compact roundabout, it will come up. There's been a few evaluations and studies done on that one there. Give you another 10 seconds to go through that one, that poll. True, false, unintelligible. And 3, 2, 1, we'll close the poll and share the results. So I can see that most people are saying that traffic signals are not safe system. And that kind of aligns with that discussion that we were having, that traffic signals are not the be all and end all. You know, they do improve safety, but they are not going to ultimately, you know, completely remove the risk of high impact crashes occurring. For those that said true, I can understand that because I did mention that they do have safety benefit. So it's not like they're making things worse, but they are doing, there is some safety improvements associated with traffic signals, so that's true. For those that are saying unintelligible question, I can respect that as well, because we don't tend to categorize things as safe system or not safe system. We don't see it as a binary concept. It just doesn't quite make sense. So instead, the language that we use is things that align well with safe system principles, or things that align poorly with safe system principles. It's more of a spectrum as opposed to being safe system and not safe system. So all of you are correct. Well done. There was no wrong answer there. I think they're all pretty fair, rational responses to have. All right, just to summarize, key points from our intersections discussion. Speed and angle, very, very important to consider what we're looking at. For impact speed, impact angle, it's going to have a significant influence on the crash outcomes. Traffic signals, I really want you to all come away to say that they do improve things. So I'm not saying don't use them, don't implement them. They definitely make things, they have an improved safety benefits, but they're not going to go all the way to virtually eliminate the risk. Roundabouts are excellent in reducing speeds, conflict points, and having that activation effect for the driver, just making them more alert of their surroundings. Raised safety platforms, also excellent to be able to wash off speed. Another thing I didn't touch on with raised safety platforms is, let's say you've got a red light runner at an intersection which has the raised safety platforms. They're distracted or whatever. They just didn't see the red light. The raised safety platform in itself, it doesn't care. It doesn't care if you're distracted or you're focused on other things or you're having a beer while you're driving, which obviously do not condone. Doesn't care about any of that things. Because it's got the ramp there, it is going to slow you down. So you could be going 70 at that intersection. The ramp will actually wash off some of your speed. So even if you're not slowing down because there's a ramp there, that ramp will do it for you. So it's a good, I guess there's a word for it, but yeah, it's unbiased as to who it influences. It's very effective treatment. And final point there, lots of secondary impacts can occur at intersection crashes. Loretta.
Couple of questions come through. First one, do we know roughly how much raised safety platforms add to the cost of construction?
I will open this up to the chat. On projects that I've worked on, the raised safety platforms are hundreds of thousands, so not millions. It's generally just asphalt, and you need to create kind of a cut-in detail of how it will tie in with the surrounding scenario.
And the next one, how to avoid the confusion of priority for refuge crossing users at the existing roundabout if we want to use safety platforms, particularly if there are 2 traffic lanes.
That's a pretty valid point. So in the scenario where we had the compact roundabout, that was a rural environment and there was no pedestrian demand or anything like that. There was no adjacent footpaths. So those raised platforms, they're not constructed with the idea that they'll be used as crossing points. If you were to have a scenario where you did need to create compact roundabouts and also support pedestrian movements, I mean, it can be done. You'd basically create the raised component as a wombat crossing. So you'd have the zebra markings there. You might also do some flashing lights or something like that, just so it's very, very obvious that it's a pedestrian crossing point. But it would depend on what type of context you're looking at. It's unlikely you'd be doing that in those rural settings because you don't have that pedestrian demand. All right, I'll move on to our next little section, which is kind of mid-block sections now. So no longer based at intersections, so mid-block. And most common crash type that we tend to see, or one of the most common, is lane departure. We have lots and lots of road that, looks something like this. High speeds permitted, and you might have a sealed shoulder, you might not. It might be straight, it could be, in a mountainous area where there's lots of curves and things like that. But anyway, the possibility for lane departure is quite high, particularly if you've got long stretches of straight where fatigue can set in, and then you've got an out of context curve, as it's sometimes referred to as. Even something as minor as this, motorists that are just used to driving straight, then just continue straight. The other type of crash that occurs here, obviously head-on crashes are quite common, but this idea of lane departure, if fatigue is setting in, because of the camber of the road, or the way that we build our roads, if you look at a cross-section, just really make that dramatic, it looks something like that, just so, you've got a crown on the carriageway, and then the water can shed off. Because of the way that it is constructed, if you've got a vehicle, driving along and then they're, oh, that looks like it's going that way. Whoops, it's going that way. If they're driving along and perhaps experiencing fatigue, because of that camber in the road, they're more likely than not dragged to the left. Yeah. So they'll get pushed off to the left. They might, potentially wake up when they're on the shoulder or just at the edge of the seal or something like that. And then what occurs is this really, really strong yank to the right. So it's referring to like a yawing type of situation, Y-A-W, yaw. Yawing is just when you've got a vehicle that is going in this kind of direction. So it's like fishtail, is what you might call it as well, or drifting. And when that occurs, even though there's not any intersections here, you can actually have 90-degree style crashes occurring. So you can have that left, sudden right, the vehicle that then's going to the right goes out in that direction. And a 90-degree crash can still occur in mid-block. Just something to be mindful of. If there's no separation between those traffic streams, those types of crashes still can occur and do occur quite commonly. But of course, we need to be considerate of the adjacent roadside and trees. There's single point source hazards, as well as utility poles, just every 40 meters or whatever. They are just point impact hazards for motorists, and they're incredibly efficient in drastically decelerating a motorist, which is not good. You don't want those drastic decelerations. You want slow, gradual deceleration. NCAP, which is the way that we assess new vehicles. They do a side pole impact crash. It used to be 29 kilometers per hour. It's 32 kilometers per hour now. In those rural settings, as I drew out there before, you can still get side impact crashes occurring. Even though it's dead straight, you'd think that it's just front-on collisions with trees and poles, but these crashes still occur, even with straight geometries. Generally, the survivable tolerance for these types of crashes is around that 30 kilometer per hour mark. So we've got, 100 kilometer per hour speed environments. Collisions with fixed hazards in the side like that, really quite low speeds before fatal outcomes occur. I've got a video of a crash now that roughly is around 60 kilometers per hour. And it is collision with this pole. It's relatively graphic, so if you did need to step aside for a minute, that's fine. But I'll just play it now. So this is a collision. Oh, it didn't work. Collision with a pole, the side of the vehicle, and just how much energy that is. So it's that dramatic deceleration. We're just going from speed to nothing to the side of the vehicle. We're just not able to survive high speeds there at all. I'll move on from that. So if you stepped away, we're going to continue. We used to have this philosophy of clear zones. And in fact, you know, we still do employ clear zones. Basically just this understanding of, we look at the edge of the road, we step out a few meters or however many meters, depending on the traffic volumes and stuff like that. And then we just make this cleared area. So there's no fixed hazards there. So there's no trees, no utility poles. Very, very much the way that all of our transport network has been constructed. But some research has indicated that, you know, regardless of how much clear zone you put, there's still a risk of run-off road crashes. And why that is the case is because vehicles can roll over within that cleared zone. Unless it's maintained, like you're constantly going out there and, you know, on the word, just steamrolling, patting down the area. It's frustrating. You know, unless you've got a really, really well marked area in that roadside, there's still lots and lots of risk for run-off road crashes, rollover crashes, graded. No, that's not the word. It was compacted roadside. That's the one I was going for. Unless you're going out there and compacting it consistently, there's every chance that a vehicle is just going to roll over in that clear zone anyway. Or the vehicle just goes on for past that clear zone that you've nominated for and collides with a tree. So say you've demarcated 13 meters, anything past that, you're allowed to put trees and poles there. Lots of vehicles run off the road past 13 meters. They can go 20, 30, 40, 50 meters past the edge of the roadside and still collide with something and still have fatal serious outcomes. So what this graph is showing is the run-off road casualty crashes per 100 million VKT, vehicle kilometer traveled. Basically just the exposure. And it's saying that, you know, providing the clear zones does offer safety benefit, but it kind of asymptotes. In other words, you get to this point and it provides less and less effect, and you're still going to have the risk of serious trauma occurring despite the clear zone that you're providing. So as I touched on, not necessarily always the safest just to install clear zones because of hazards beyond that clear zone or rollover crashes occurring. Once again, I just want to validate that it's still improving safety. If you don't put trees a meter from the edge of the seal, that's a good choice. So 50% CRF, creating the first 4 to 5 meters. But what is more effective, actually, before I get into that, here's a photo of, you know, the Hume Freeway, which probably looks quite similar to how we've got lots of our national highways, national freeways, our motorways, looks something like this, which is basically nice wide traffic lanes, nice sealed shoulders, divided carriageway. It's enough, you know, a width there that has been calculated to hopefully reduce the risk of head-on crashes. But this looks quite similar to lots of our national highways. Instead, if this were to be built now, we would instead edge barrier the whole side of the carriageway and then median barrier right down the center there, which actually means you can have less of an envelope because you don't need such a wide median there if you just put in a barrier system. And the reason for that is because barrier system technology has dramatically improved over the years, the decades, and they're much, much better at containing and slowing down vehicles so that it's survivable. The Hume Freeway that we're looking at here, this was taken about 10 years ago, this photo. Since then, the whole Victorian section of the Hume Freeway is continuous barrier. So on the edge, on the median, barrier systems. It has been transformed since the initial construction. The Austroads Guide to Road Design Part 6. This is where you'd get all your barrier information, and it talks about that clear zone and how we're moving away from that clear zone approach or just solely relying on it. It's basically saying that it is much safer to put in a barrier system that's designed to contain errant vehicles at 4 meters from the edge of seal than to create a clear zone that's 50 meters wide. Like, it is much safer to put in a barrier system. So although clear zones still, have merit and things like that, where you're able to put in barrier systems, you'd probably prioritize that as an investment. We've got a diagram now of some general alignment with safe system principles. So once again, it's not that binary concept of is it safe system or not. It's a scale, it's a spectrum. And what we know works very well is barrier systems on the edge, barrier systems in the middle, and also providing shoulders and things like that. So full containment. Where we're unable to get those and we've just got substandard, perhaps gravel shoulders or no shoulders, narrow traffic lanes, that aligns very poorly with safe system principles. Ideally, in those scenarios, we would have lower speeds. So it's kind of bizarre that the default speed can apply to something, a road environment that looks like that, and the default 100 kilometers per hour can also apply to something that looks like that, when there's very, very different risk levels associated with both of them. So happy to facilitate high speeds in these types of setups. Not as confident running high operating speeds where you're unable to protect drivers from head-on collisions, but also from run-off road type collisions as well. Loretta.
Yeah, just a question that's come through. Why would 1+1 full containment be deemed lower in safety than 2+2 full containment? Would it be because if there is a crash, there is nowhere for following vehicles to veer to?
Oh, I love it. Ask the question, answer the question. That's great. We'll give a prize out there. Another reason that this one would be slightly lower, and there is a little note there that it's just general advice only, so take it with a grain of salt. The reason that that one would be lower, so yeah, if there's a crash there, have you just created a massive traffic jam? How do people get around? The other reason is allowing overtaking opportunities, because if you are stuck behind a caravan or whatever it is, a slow vehicle, and you want to get around, the containment, the barrier systems basically create a tunnel. So if there's a slight gap in the barrier system, it could be an opening at an intersection. You might get a vehicle that's trying to overtake at that section and then trying to get back into the lane before the barrier system starts again. So it's not quite as ideal. Generally, what is implemented in those scenarios is the 2+1 arrangement, which is you've got overtaking opportunities on this side of the carriageway, might run for a couple of kilometers and then goes back to single lane, and then that overtaking opportunity starts on the other side and it just continues to go back and forth. So 2+1, that's a more common type of arrangement. Good question. All right, I'm gonna motor on through these last few slides to make sure we get through the assignment as well. We've just got some more cross sections. This is taken out of IRAP, which is just risk assessment program, a star rating system for roads. 4-star road would be more conventional or historically the way that we've built our carriageways. To get to a 5-star road, we need to see barrier systems on the edge as well as the median as well. I'm not going to go through all of these different cross sections, but just some food for thought as to what they could look like and the different star environments. One thing really worth mentioning though is if you are doing edge containment, thinking about what type of width you're able to achieve, because if you're not wide enough and you do have a vehicle that's broken down and they're unable to pull off the live carriageway, surely you can appreciate why that could be a risk. So if you're unable to achieve, the full width there to be able to house a parked vehicle, generally what you would do is create breaks in the system so that this broken down vehicle can aim for that break and get off the carriageway, because you don't want to create rear end collisions here. All right. Just wanted to touch on another neat little treatment, which is referred to as a Raptor crash cushion. It's a proprietary product. And what we had here, this is in the township of Mildura, so like a rural town up in Victoria. Some young males driving at 2 a.m. Approaching this roundabout, potentially under the influence at high speeds, goes through the roundabout, and they collided with a utility pole. This was no ordinary utility pole. It's got this little protection device around it, which is referred to as the Raptor crash cushion. This is another image of what it looks like. And it's actually designed, so rather than just a single point hazard, it's designed that as you come into contact with it, it kind of swivels or rotates around. So it's saying, nah, don't come near this pole, go away. And it slowly pushes drivers away from that thing. Quite an effective device. Unfortunately, utility providers are not overly enthusiastic about you touching their pole. It can be really hard to have these discussions and say, I want to put a Raptor crash cushion here because of the risk. Sometimes utility providers are like, nah, I've got assets I need to get to. Don't put it there. But in terms of safe system thinking, and if you're completing a safe system assessment, by all means recommend these as possibilities because they do offer safety benefits. Quiz time. We've got another quiz, another poll, please, Loretta. I can see the question, does it affect the maintenance of utilities? To some extent, yes. But at the same time, it's not as if the Raptor cushions are permanent fixtures. You just need to unbolt it and then you can go out and dig whatever's underneath there. So it's not like an onerous activity. True or false? Sealed shoulders improve road safety. I'll give you 20 seconds. Yeah. 5 seconds. 4, 3, 2, 1. And we'll close the poll and share. And I can see that, yep, 90% are saying that that's true. And I agree with that. They do improve road safety. So in this one was a bit of a trick. So the previous one was saying, is it safe system? Where it's not a binary concept. Improving road safety is a pretty standard way of saying things. So sealed shoulders would improve road safety. I don't think that's an example of an unintelligible question. I don't think. Unless there's something unintelligible that I have not noted and you want to tell me in the chat, by all means. Just to close off this discussion for mid-blocks, you know, to achieve high alignment with safe system principles, it's basically barrier systems, full containments, continuous barrier systems. Clear zones, they do reduce risk. They do a good job of that, but not as well as barrier systems. The aspirational cross sections that we just jotted through then, that's more futuristic planning, strategic planning of future road environments, but also how you could potentially upgrade or transform existing networks to look like that aspiration. Loretta, are you okay if you take the reins now and talk us through what's next?
Yeah, sounds good. All right, well, I guess I know everyone has, logged into the LMS. You would have seen that on Tuesday with Marissa. So I hope you can see my screen now. Max, can you see that? Excellent.
Clear?
All right, so just going back into the LMS, you'll notice, down the list, we're on module 2. So in the module 2 section, lots of different resources that you can reference here. But what the tasks are for this module is, firstly, there's a quiz. So ensure you click on that and attempt that quiz. So you're just clicking on there and going through the questions. And the second thing is an assignment. So basically what we've covered today. So on the likelihood, severity, and exposure. So I'll go through sort of what you need to do in this section, and then Max, I'll get you to run through the assignment in a little bit more detail. So just here, you click on this PDF. So this is your actual assignment. Once you've completed the assignment, please ensure you save it. And then in order to submit it, you do need to click on Add Submission. And you simply just drag it into this folder, or you can find it through the Files section and save. I might just quickly note those that work for Transport for New South Wales and perhaps some other organisations, you might have firewalls that may not allow you to upload it and add the submission. So don't stress, just simply email it to me or to the team at training and we'll upload it for you on your behalf. So pretty simple, open the assignment, it's a PDF, save it, drag it in and add your submission. So this is basically the assignment. So Max, I'll get you to run through this if you like.
Thank you very much. So we've got the instructions there listed at the top. You basically get to pick any intersection. It can be a signalized intersection, it can be a local intersection. Pick something you're familiar with, pick something that you hate driving through, or you hate, whatever. Do anything that you want to. Can be a random one as well. We'll get you to fill in your name within this document, and then also just give us a link to whichever intersection that you pick. So go onto Google Street View, copy the URL, and then paste it in there, just so that we can have a look at the same intersection. You don't have to go out there on sites. So that's all sweet. So can you go back up to the top, Loretta? Still going through the instructions. I'm not as familiar with this assignment. So you just need to inspect the intersection via Street View. Don't worry about getting boots on grounds. Then we just get you to fill in the table that's on the second page. All we're looking at are factors associated with exposure, likelihood, and severity. And then we're also saying one thing that could be implemented to reduce the impact of each of those elements as well. So Loretta, if you could scroll down, we'll have a look at the table. So we've got 2 rows there. The first row is saying, give us factors that increase or influence exposure. Right? So in that little box there, we'll get you to say a minimum of 1, a maximum of 3 things for that. Dot points is completely fine. Please do dot points. Same discussion if you go across to the right for likelihoods. factors that increase or influence the likelihood. Same for severity, right? So all we're going to be marking you on is, are you correctly categorizing factors associated with exposure, likelihood, severity? Same exercise, same thinking, but now what would be reducing the impact of exposure, reducing the impact of likelihood, what would be reducing the impact of severity? So it needs to be broken up like that. We want to see what are influencing or increasing for the top row, and then what is decreasing or reducing for the bottom row. Once you've done all that, save it, upload it as Loretta showed you. We're not expecting you to write War and Peace for this. Dot points is fine. I reckon allocate about 15 minutes. If it's taking you longer than half an hour, it's probably too long. So just give us a call. We'll chat through it, make sure you've got the right scope. Yeah, that was it. That was it for me.
Perfect. So yeah, so once you've filled all that in and save it, and then yeah, add your submission in here. Yeah, shouldn't be too hard, but if you've got any issues with anything, please feel free to email me. I'll help you out as best I can, or pass it on to someone that can. Max, I had one question earlier, which we sort of passed through. Is it okay if I quickly ask you that question?
Sure. Just before we move on, when's this one due?
Oh, sorry, it is due on Tuesday. Thank you. So just due on Tuesday, before, if you can do it sort of before the next module, we might actually sort of, run through a few of those, but we'll see how we go.
And yeah, question time.
So the question earlier was, is the reduction in risk caused by the reduction of the number of conflict points offset by the increased number of vehicles going through each conflict point?
I'm guessing that's to do with the roundabout or the compact roundabout. And yes, the reduction is to do with the conflict points, but also the impact speed and the impact angle. So it's multifaceted. There's many reasons why roundabouts are more favorable compared to traffic signals.
Another question in regards to the assignment, Ben has asked, should we choose an easy or complex intersection?
Ben, if you're feeling courageous, go and pick the hardest intersection, that 5-leg intersection that's really wacky. But if you want to pick something more local, by all means, whatever works for you, we are happy to review. Yeah, easy.
Excellent. Well, thank you. It gives you a little bit of time to start on maybe the quiz if you've got a few minutes up your sleeve. But thanks, Max.
No worries. I look forward to seeing you all next week. I hope you all have a lovely weekend. Stay safe. And yes, thank you, Loretta. Enjoy your day.
Thanks, everyone. Bye.
Bye.